In a simple linear regression model, we assume that the residual error is normally distributed with an expected value or mean of 0. This means the conditional mean or the expected value of y given x is equal to b0 plus b1x. If x equals 0, then expected value of y is equal to b0. This means the intercept in a simple linear regression model is simply defined as the expected value of y when x is 0. On a line-fit plot, it is the point where the regression line interacts with the y-axis. In the context of our study, where y represents a student's final exam score and x represents hours studied, an intercept of 45 indicates that a student who has not studied at all is expected to score 45 on the final exam. Now, let's consider the expected value of y when x increases by 1 unit. The resulting change in the expected value is the slope. This means the slope is the expected change in y for every 1 unit increase in x. In the context of our study, a slope of 5.5 represents that for every additional hour a student studies, their expected final exam score increases by 5.5 points. However, the interpretation of the intercept is not always meaningful, and the interpretation of the slope differs if the independent variable is discrete or dichotomous. For instance, predicting a person's height based on their weight, the intercept is not meaningful because it represents the predicted height of a person who weighs 0, which is impossible. And if the independent variable is dichotomous variable, the slope is the expected difference in y between the two categories. For a discrete variable, the slope is the expected change in y for each 1 unit change in x, whereas for a continuous variable, the slope is interpreted as the rate of change.